All right, so thermodynamics has to do with the study of the relationship between heat, work, temperature, and energy. And before we actually talk about the first law of thermodynamics, let's quickly look at the concepts of a system and surrounding. So we can represent the description of a system and surrounding with this image. So let's say this is the system, and the one outside of it is the surrounding. So a system is that matter that is understudied. So in chemistry, we are very particular about the system. So the surrounding, however, is everything all around the study, all around the system rather. So the surrounding is not understudied. So suppose we have a given system of a gas which is composed of a moving piston and the cylinder. So let's say we have this, and this is a cylinder. So let's say this is the piston, and so these are the gases inside of it. So this whole setup containing the gas can be taken as the system. So let's say the volume was taken to be V1, right? So this is a moving piston. So the force tending to compress this gas or move the piston downward is an external force. So we have this external force here moving the piston downward. And this external force gives rise to external pressure, right? So when the gas is compressed by an external force, we simply say that work is done on the system. So if we have a force or an external pressure that moves that causes a compression in this system, then work is being done on the system. So the internal forces exerted by the gases, we have gases inside of this system. So the exact forces by themselves. So the forces that these gases exert are called the internal forces. So let's say F internal, right? So according to the first law of thermodynamics, when work is done on a system, the work is positive, right? So these internal forces generated by the gases also do work on the surrounding. Like the external force is doing work on the system also is doing work to the surrounding by the internal forces. So the work done by the gases on the surrounding is taken to be negative. So let's talk now about the first law of thermodynamics. So according to the first law of thermodynamics, the internal energy of a system can actually be increased either by adding heat to the system or by doing work on the system. So recall that internal energy used to be the sum of the potential and the kinetic energy, but we can actually change the value of internal energy as a result of two separate type of energy transfer across the boundary of the system. So this is internal energy of the system. Q is the heat system and work system. So notice that everything in this equation is expressed in terms of the system. So now let's talk about the sign convention of this first law of thermodynamics. Okay, so because we are dealing with the system in chemistry here, so if it's, so let's say we have this, right, before we start talking. So let's say this is the system, right, and everything around it is the surrounding. So we have the surrounding outside of it. So because we are dealing with the system here, if it is transferred to the system, let's say we have it transferred here. So this it um will take a positive sign because it's transferred to the system. The system has the heat. That is, you transfer the heat to the system rather. So when it is transferred out of the system, we have it to be negative. So yeah, we have it to be negative. So let's say we specified in a given question that a gas system absorbs 35 joules of heat. So if a system absorbs 35 joules of heat, that means we are taking heat into the system, and that will be positive um, 35 joules, right? So, but if the system is losing out the heat, So you expect this to be negative. So that is that. All right, so now let's go back to this. So we say that work equals to negative P external change in volume, right? So this is the formula for calculating work at constant external pressure, right? So under compression of the gas here, work done on the system is positive because the change in volume at that condition is negative. So now let's look at it. No, this is a system of a gas. When you compress the system of the gas, you expect that the system to become something like, let's say this was the initial volume. You expect that the volume should decrease, right? So we have V2 to be lower than V1. So therefore we have this to be negative P external, and then you have V2 minus V1. So because the final volume is lesser than the initial volume, everything here will become negative. So when you multiply this, it gives you a positive sign. So because of that, the work done on a system is positive. On the other hand, when under expansion of this system, the work done by the system is negative. So this is because the change in volume under expansion is positive. Like the final volume would expand more. Like, I mean, the final volume will be higher than the initial volume. So you expect V2 to be greater than V1 under expansion, right? So because of that, this one remains positive. So the whole work done is negative. So therefore, we can simply say that under expansion, we have that V2 to be greater than V1, right? And work is therefore negative. Under compression, when we have compression of a gas, we have V2 to be less than V1, and we therefore have that work to be positive, right? So, so we've already established that work done on a system is positive, and work done by the system to the surrounding is negative, right? So we have two profound equations for work in the first law of thermodynamics. So these two equations for work are, we have the first one to be work equals to negative P external, then change in volume, which was what we talked about in the previous explanation. So we also have work. Work can also be negative 2.303. There's a point here, nRT, and then we have log V2 over V1, or you simply say P1 over P2, like log P1 over P2. Recall that from Boyle's law, pressure is inversely proportional to volume. So V2 here, when you are changing this to pressure, we have P1 instead at the top. Recall that thermodynamic processes are isobaric, we have isobaric, we have isothermal, we have isochoric, we have adiabatic process, and we have all of that. So but these two formula for calculation of work remains. It's just that we need to clarify which one to use at the right time. So when the question says constant external pressure, so always look out for this in your question. Once it says constant external pressure, simply go for work equals to negative P external change in volume. But once the question says reversible, so we can either have reversible isothermal process, or we can also have irreversible isothermal process. So recall that isothermal processes are constant temperature processes. So at constant pressure, that's like isobaric, right? So if you also see isobaric, definitely This is the formula. This is the right way to calculate your work. Constant external pressure, just use this. But when you have reversible isothermal process, so the reversible isothermal process, you use negative 2.303 nRT log of P1 over P2, or log of V2 over V1. So also when it is irreversible, take note of that. Irreversible isothermal process, you simply use work equals to negative P external change in volume. So now it's important to note the unit of work you are working with. So the SI unit of work is actually joules, right? But in most cases, pressure and volume are always given in liter and ATM, right? So pressure most times will be given in ATM, and volume in most time will be given in liters. So let's say in a given question that involves the use of this particular formula, the pressure was given as let's say 2 ATM, and the volume was given as 10 liters, right? So if you are told to like calculate um, the work um, in this process, actually what you need to do is therefore going to be work equals to negative 2 ATM, right, times 10 liters, which is equal to um, negative 20 ATM point liters, right? So this is not equivalent to 20 joules. Take note of that. This is not equivalent to 20 joules. So we have, let's come up here. So we have that one ATM, please take note of this. One ATM dot liter equals to 101.3 joules, right? So once you have your answer here, for you to convert this to joules, you simply multiply this by 101.3 joules, and then you get your final answer. Please take note of that. And also, 1 calorie, if you are told to convert your answer to calorie, 1 calorie equals to 4.184 joules. So you need to take note of this. Thank you. All right, so let's look at this question. So calculate the pressure work done when the pressure volume work done when a system containing a gas expands from 1 liters to 2 liters against a constant external pressure. So we need to take note of the fact that the gas is expanding. So, and we may want to assume that the work should be negative because the gas is doing work on the surrounding. So, and constant external pressure also here is 10 ATM, right? So this is telling us that the formula to use for the calculation of work should be work equals to negative P external, then change in volume, right? So we therefore have that work equals to the pressure in ATM is 10. So we have 10 ATM, and the change in volume is 2 minus 1 liter. So basically we have minus 10 times 1 times 1. So we have it to be negative 10 ATM liter. So recall that 1 ATM dot liter equals 101.3 joules, right? So 10 negative 10 ATM dot liter would give us x here. So let's cross multiply. Therefore have that x equals to negative 1.013 joules, right? So the question says we should also calculate the work done in calories. So for us to calculate this, we have that 1 calorie equals to 4.184 joules, right? So let's put this here where it belongs. So we have negative 1013 joules, and this as x, right? So let's cross multiply. So therefore we have that x equals to negative 1013 over 4.184. We have this to be negative 242.1 calories. So this is the answer. So let's also look at this question. So one of the moles of an ideal gas at 25 degrees Celsius is allowed to expand reversibly. So take note of the fact that it's expanding reversibly, right? So it's expanding. So the work, we might assume that the work may be negative, right? So and reversible expansion. So we're basically using this work to be negative 2.303 nRT. Then we have log of P 1 over P2 or V2 or over V1 depending on the one we are given. So but for us to confirm that this is the formula we are using, we need to also see the constant temperature air. So reversible constant temperature. So this confirms that this is the formula we're using for the calculation of work. So and we are given a liters not in volume, not in pressure. So we have to use the latter one here. So we have that work equals to negative 2.303 times 1 mole, right? 1, that's n is number of moles. So R is 8.314, right? And our T, which is the temperature, is 29.8 Kelvin. Recall that this Celsius has to be converted to Kelvin, and we have it to be 25 plus 273. So we have 29 um 98 Kelvin, right? So the next thing we need to look at is the aspect of log. So we have log of we're not given pressure but are given volume. So the final volume is 20 liters, so over 10 liters, right? So this cancels this and we have 2 air. So we therefore have this to become negative 1717.63 joules, right? So we need to convert this to calories. So the work done in calorie can be expressed as work on 1 calorie equals to 4.184 joules, right? So we therefore have that negative 1717.63 joules x here. So when we cross multiply, we have x to be equals to negative 410.52 calorie.